My name is Vaibhav, and I'm a technical director at Pixar Animation Studios. I've worked on the lighting and rendering optimization team on Coco, Incredibles 2, and Toy Story 4. Today, I'm excited to talk about how machine learning has made an impact in animation and go in depth into a project I've been working on, Deep Learned Super Resolution, which uses generative adversarial networks to reduce rendering time and produce high-resolution imagery. But first, I want to start off with an overview of the filmmaking pipeline. I know we have folks here from many different industries, and it's good to get an idea of what are the different problems that need to be solved to create one of these incredible films that capture the minds and hearts of millions of people around the world. Let's kick it off with story. Many years before a film is released, a filmmaker will come up with an idea, a set of characters, conflicts between them, the setting, and theme. They eventually get to a screenplay and sketch storyboards to figure out how these characters think, interact, and feel. This is all careful planning before a ton of artists and engineers come together to bring these characters to life in a virtual 3D world. Next up, we have characters and sets. We have modeling artists using computer-aided design software like Maya or ZBrush to create the 3D geometry associated with every character and set piece. All this art is described with math, using vertices, edges, and different transformations. And the technology is so advanced that artists can design fine details like strands of hair or create an enormous forest by instancing just a few trees. From here, shading artists design the surface of each piece of geometry. We have hair, skin of different colors, various patterns of embroidery on clothes, and so forth. It's incredible the vast array of real-world textures artists can capture in a computer by using physically based models to simulate how light bounces off different materials. Next, let's talk about layout. Once we have the characters and set pieces, layout artists arrange these elements for every shot. They select the camera and lens and think about the composition of the scene and depth of field. From here, we have animation, which is by far the most labor-intensive part of the filmmaking process. Animators need controls to animate a character. So we have special rigging artists to create these controls for every limb, for every finger. On the face, we have the eyebrows, eyelids, lips, and jaw. Our animators use these controls to create animation at 24 frames per second for a 90-minute film. All these details matter to create a compelling performance that the world keeps coming back to see. You can imagine the job gets really fun when they try to figure out how to animate animals, like dogs and cats, or even non-living characters like robots. So this is a uniquely challenging and satisfying job. Next up, we have simulation and effects. From Merida's hair to rain droplets to Violet's force field, these artists and engineers know how to observe and bend the rules of physics to produce all sorts of phenomena that are critical to telling the story. From here, lighting artists must place virtual lights in the scene, much like in a live-action production, except in a virtual world, you have so many more possibilities and much greater control. You can precisely set the number, color, position, and intensity of lights. You can turn off shadows or make lights only affect certain objects. There's so much we can do with lighting to further the director's vision. Looking at this before and after, you can see just how important lighting is to creating the final output. My work at Pixar is related to lighting and rendering, and in just a moment, I will be elaborating more on how my work in AI is impacting this stage of the pipeline. Next up, we have sound. Typically, a lot of voiceover work is recorded on site, and it takes quite a bit of precision from the animator to synchronize the lips of the character with the voice actor. And of course, there's also the film score. Some of the most iconic moments in film are so striking precisely because of the score. Depending on the composer and genre, software instruments are combined with live orchestral instruments and vocals. For decades, technology has been deeply embedded with sound and music creation, and now a lot of interesting research is happening with AI-based sound synthesis. It will be interesting to see what makes its way into production. Finally, we have image mastering. This is the final step before the film is released into the world. Their work involves color grading, creating multiple formats like HD, Ultra HD, and high dynamic range, as well as creating international versions in different languages. So that gives you a sense of the filmmaking pipeline. There's also marketing, theme park deliverables, legal, and more, but this covers most of what's involved in creating the content. So now let's talk machine learning. One example of machine learning you will find in some of the most successful films ever made, the Avengers series. To animate the character Thanos, the VFX studios used the Medusa performance capture system from Disney Research, and machine learning was used to process that motion capture data and obtain high-resolution geometry. Of course, no one advertises the incredible technology. People just want to see Thanos conquering new worlds. Another example of machine learning gaining widespread use is in image denoising. Rendering a single frame for a movie involves a computationally expensive process called ray tracing, which simulates how light bounces around in a scene. When you start a render, you observe these really unflattering noise artifacts that you can see on the left. As you render for more time, the image converges and the noise level progressively reduces until you can't notice the noise anymore. The idea behind denoising is to render for less time and have the denoiser predict the clean image given the noisy image. This technique was fruitful on several of our recent films, and some of my colleagues helped bring this technology into production. But of course, as rendering becomes cheaper with better technology, artists often eat up those gains by trying to push creative boundaries. More lights, more geometry, more fog and volumetric effects, more complex lighting. All this often results in longer render times. And of course, there's perpetually a demand for more content. So there's still room for innovation to make rendering cheaper. We've taken an overview of the filmmaking pipeline and looked at two ways that machine learning is already impacting the industry. Now, I want to talk about an emerging technology that I've been working on, deep learned image super resolution. The basic idea here is that we're taking a low resolution image, you can see here on the left, and we expect the AI to give us the high resolution image on the right, with all the fine details that we love. So why is upscaling helpful? Well, it can be used to create high resolution content, but the quality from traditional methods like total variational inpainting is not as detailed as we would get from deep learning. We upscale instead of render at high res because high res rendering is cost prohibitive at scale. I mentioned just how expensive ray trace rendering is. Just to give you some numbers, it typically takes at least 50 CPU hours to render one frame at 2K resolution. We render 24 frames per second for a 90-minute film and render each shot many times as the artists iterate. Further, we have multiple films in flight at a given time. All this adds up to a lot of demand for render farm, which is a finite resource. If we render at a higher resolution like 4K, that's 4 times the pixels and more than double the cost. So upscaling techniques can allow studios to deliver high-res imagery without blowing up the cost. Further, rendering at a smaller resolution incurs a reduced memory footprint, which can further optimize render farm utilization. So to summarize the objectives, using deep learning, our goal is to first replace parts of the pipeline where old upscaling techniques were used, resulting in a higher quality product. And second, we hope to introduce deep learned upscaling to new parts of the pipeline, which would allow us to make the same content at lower cost by enabling us to render at a lower resolution. We start off with a literature review. I examined what is the state of the art for super resolution tasks. One interesting thing I observed is that deep learning has come a long way when it comes to 2D image space operations. Ever since the ImageNet dataset came out and deep convolutional networks were found to be effective for image-based problems. Specific to SuperRes, I observed from R&D efforts by the Disney Research Group that the best results are produced by GANs, generative adversarial networks, and perceptual loss functions. These really boosted the quality, sharpness, and richness of the textures in synthesized images. Based on my review of this work, the state of the art is using a deep convolutional residual network with adversarial training and a perceptual loss function. So my task was to get a training pipeline running using the state-of-the-art ideas, and then address any gaps in the research that we will need for production. As part of this project, we collaborated with Disney Research, and it was a huge advantage being able to source ideas from them. So let's talk about data. Basically, what we want are pairs of low-res and high-res images. One idea is using existing high-res images that are already rendered and then downsampling to get the low-res. However, we observed that the relationship between a high-res image and a low-res image is a very complex nonlinear function, and there's no existing downsampling operator that can do this. Research to circumvent this problem is ongoing, so instead we render pairs of images using RenderMan, the rendering software Pixar uses for all of its films. We render pairs from many different shows, and we include scenes with diverse lighting, characters, strength of film grain, textures, and so forth. The richer the dataset, the better off we are. From there, we write scripts to gather the data into one place and keep only pairs that are coherent, because there can be lighting and shading differences due to resolution-dependent parameters that can make some pairs unusable. And through this process, we end up with about 3,700 pairs. So how do we train this thing? In terms of hardware, we set up a massive Linux instance with NVIDIA GPUs with the help of our systems team. In terms of the development environment, we built a Conda environment with PyTorch with the help of the tools build team. From there, we implemented the training pipeline in PyTorch. For fast I/O, we store the training data in a Lightning memory map database, which reduced training times by almost 1/3. One thing that's unique about SuperRes and working in image synthesis in general is that we can't just trust the error metrics like the PSNR score. An image might have low error, but reveal unwanted artifacts or smooth out useful details. Another image might have higher numerical error, but show more visually pleasing results. Improving error metrics to match how a human would perceive an image is an active area of research, but for the purposes of this project, I made sure to visually inspect the validation images when evaluating an experiment. I wrote custom Python scripts to make it easy to view images and compare different experiments, which allowed me to make decisions on hyperparameters and architecture and so forth. Recently, we started using the DGX2 supercomputer to run SuperRes training experiments. This machine has 16 GPUs, and the training time right now is around 50 hours on 4 GPUs. It was a huge advantage having this resource to run multiple experiments at once. It helped me make discoveries and address artist feedback much faster. And as a general rule, if you're trying to train any custom machine learning model, aggressive experimentation is a very important part of the process to get the most out of your project. From here, I want to talk about some of the unique challenges of deploying this technology into production. First off, most deep learning work in computer vision deals with images with luminance ranges between 0 and 1. But in the pipeline of making a feature film, we often deal with images with high dynamic range data, much greater than 1. For example, when rendering the sun or a light bulb. Because neural networks perform best on data that is normalized between 0 and 1, or -1 to 1, for SuperRes, we basically transform the data into log space before feeding the data into the network, and then transform the output back into linear space. And that's how we support HDR. Next up, when we were getting feedback on our initial results from the studio mastering team, they observed very subtle color shifts in the SuperRes output. The colors would be slightly off. You're seeing an exaggerated version of that on screen. We looked at this and noticed that the perceptual loss in giving sharpness also sometimes slightly changes the color beyond what the artist intended. To solve this, we could have reduced the weight of that hyperparameter to reduce the color shifts, but then we would also have lost some sharpness, so that wouldn't work. Eventually, someone on the team came up with the idea of adding a new loss term that penalizes the difference in the color in a low resolution space. And we haven't seen any of these color shifts since then. A third issue that came up was unwanted noise and over-sharpening of the input. You can see a little extra noise here on the balloon up top. We noticed that some of our initial hyperparameters push sharpness a bit too far relative to what the artist wanted, reducing the feature loss and GAN loss while boosting the content loss helped reduce the extraneous noise. A lot of artifacts we observed from initial versions of SuperRes, color shifts, noise, edge artifacts, they're often quite subtle. Most people in the audience would get so lost in the story that they probably wouldn't notice. But of course, Pixar artists are very precise, so we had to fix them. And as I mentioned, it took a lot of experimentation and iteration to get anything close to what would be considered production ready. Another unique challenge with filmmaking is handling channels beyond red, green, and blue. Most computer vision work just deals with those three channels. Fortunately, the number of input and output channels in neural networks is a simple tunable parameter, and for additional channels like alpha, that was sufficient to get us something that we could start testing with. A lot of fascinating research stays as research, but I'm excited to share that SuperRes is now part of our pipeline and is starting to find usage in our productions. I wanted to leave you with a few points that could be useful in your organization. I first came up with the idea to pursue super resolution about 2 years ago by paying attention to work coming out of Disney research and thinking about the connection with our production pipeline. What could that journey look like for you? Well, I would recommend taking a look at the titles and abstracts of some of the leading journals in AI. NeurIPS, ICML, CVPR are among the best. For computer graphics, SIGGRAPH is the leading venue. And from looking at the recent papers, you can tell there's a lot of work being done at the intersection of graphics and AI. Of course, most people are not technical enough to read through all the math, but looking at the headlines, you can see what the technology can do today and where it might be headed. And looking at the authors, you can see who are the leading actors in these fields. Once you know where the research is, think deeply about what problems your organization faces and come up with unique solutions. A second takeaway is to promote a culture of risk-taking in your organization. One of my observations at Pixar is that folks are open to new technologies and experimentation early during the development of a film. But once we're deep into production, we instead focus on stability and try to avoid the technology breaking. If you can find that balance between risk-taking and tried and true processes, you can successfully innovate and mostly avoid chaos. A related idea that's personal to me is that through this project, I was able to align what I was passionate about, AI and graphics and creating new technology for artists, with something that the company needed. We were already doing upscaling before, it's just that the quality could be a lot better with AI. Similarly, when you're working for a company, be thinking for yourself, what does my organization need to be successful? And how can that gel with what I'm excited about, or good at, or want to learn more about? This line of thinking was really important for me. Just to cap this off, the legacy of animation is the 2D hand-drawn animation that Walt Disney was famous for, going back as far as the 30s when Snow White came out. In the 90s, computer animation changed the game forever, creating so many new possibilities for artists and technologists. Now with AI becoming mainstream, we're just starting to discover how this new technology can enhance the way content is made and experienced. And I'm really excited to be part of this revolution in a small way. I want to thank the Pixar research team, systems, build and release, mastering, lighting, rendering, as well as the studio leadership team for giving me the time and space to pursue this work. And special thanks to Mark Meyer, Jeremy Newland, and Chris Shores, who have been my closest collaborators. That's it for me. I hope you learned something new. Thank you for tuning in.